I think in the last few classes on Java, we had talked about the different kinds of ways to create a constructor. We had also talked about instantiation. Then we had seen what is the meaning of the default constructor, a constructor with parameters, and that kind of thing. Now we will step back a little in this course and talk a little more about what we mean by the primitive data types of Java. We'll talk about the different kinds of primitives in Java. Then we'll talk about the difference between a primitive and a reference, and then we'll talk about how do you combine operators into a equation in an expression. So let's start very simply. So what are the basic or fundamental data types that Java provides? There are about 8 fundamental data types that Java provides. They are basically classified into 2. One are called integer data types, and the other are called floating point data types. Actually, there is a data type called char, which is could be integer or could be which is neither integer nor floating type. So the char data type is about used to accommodate basically 2 bytes at one shot, which is basically it can be expanded depending on the language, because in Java there is support for internationalization. Now the important thing to remember about the char data type in Java is, unlike other languages like C and all, where the char data type is only a single byte, that is 8 bits, the char data type in Java is 16 bits. Now that's a very common question as to why is it so. Reason is languages like C, C++, which have the char data type, they were created when there was no need for internationalization. There was no need to support other languages. So in order to support the ASCII character sequence, 1 byte or 1 character, that is 8 bits, was enough to accommodate the ASCII code. But with the starting of Java, like any other new generation languages, the proposal is that we should be able to accommodate not just English, but Arabic, French, Devanagari, any number of languages into the Java language. If you need to do that, then your character obviously can't be just 8 bits, it needs to be 16 bits, because you need to support a lot more codes beyond the ASCII code of the English language. So if you have to support more codes, you obviously need a bigger size for character. So it's important and worthwhile to remember that a character data type is 2 bytes in size in Java and other internationalized language as against the other languages. So the other data types are, there is the regular byte data type, which obviously is 1 byte in size. Then there is a short data type, which is 2 bytes in size. Then there is the int data type, which is, so byte is 1 byte in size, short is 2 bytes in size, int is 4 bytes in size, long is in 8 bytes in size. In the floating point, there is float, which is 4 bytes in size, and there is double, which is 8 bytes in size. Now a little, so basically we have these 7 data types, and obviously you have the Boolean data type, which is used to represent true or false. So I'm keeping char and Boolean a little out because they are in a way different. Boolean can take only 2 values, which is true and false. Char obviously is used to represent text character data, so that belongs to a separate family. So we have byte, which is 1 byte in size, short, which is 2 bytes in size. Now another important thing to remember is, and I'm sure when we talked about languages like C or C++, we always used to make a statement that there is a size of operator which is available on all these languages, which will tell you the actual size on a given machine of a particular data type. What I'm trying to say here is that if you take an int data type in C, the size of the int data type could be on some machines 2 bytes, on some machines it could be 4 bytes. That would happen with C or C++. That will never happen in Java, because these sizes are implemented not actually by the operating system but by the Java virtual machine. So the Java virtual machine is very strict as far as sizes are concerned. So whether your C may have an int which is 2 bytes or 4 bytes, but that will never happen in Java. In Java, these sizes are fixed. That is, anywhere in the world, on any platform on which the Java virtual machine is running, the long will be always 8 bytes, the int will be always 4 bytes, short will be 2 bytes, byte will be 1 byte, and a similar way float and double. Now, the way the float 32 bits are structured, they are broken into what is called as the mantissa and also called the exponent. So basically they are certain base to the power of an exponent. So there is a provision for an exponent to be part of float. In fact, the exponent is about 8 bits and the float is about, the base is about 24 bits. So that can be a breakup. So a float, though it has the same size as int, because of the ability to raise to a power, the int or for that matter even the long has a value lesser, ability to hold a value is lesser than in a float. Now this is very important to understand that a float can accommodate bigger values than long, because float has a provision for an exponent which long doesn't. Long cannot hold 10 to the power of something. The exponent value is possible in a float and possible in a double. So from a logical sense point of view, the way these are byte is smaller than short, short is smaller than int is smaller than long is smaller than float, and float is smaller than double. This is very important to remember in a consideration that we are going to soon have, which is called narrowing or widening. We are going to see what are the problems which come because of this and how to resolve them. But this is very important to remember, this kind of a sequence of sizes. It's crucial that we remember this. That byte is smaller than short, that is not a surprise. Short is smaller than an int, I don't think that's a surprise either. Int is smaller than a long, that's not a surprise either. But long, though it is 8 bytes in size, is smaller than a float, because float has an exponent part which is not there in long and which is shorter than a double. So this is very important, and a lot of people get confused about this part wherein we say long is less than float. So this is very important for all Java programmers to remember. Now what we are going to do is we are going to talk about how primitives work and what actually happens when the primitive is used. So for doing that, let's write a bit of programs in order to appreciate how the primitives work, how their things are brought together, and we'll take a small example, do it, and then we will elaborate on this. So we are creating a small file called vi primitive.java. As you can see here, we are creating a small file called primitive.java, and let's get down to its creation. So we'll create a small program with the class called class primitive. Let's everything in Java has to be a class. We can't have just functions or main sitting there. So we are creating a class primitive for lack of a better name. So we are saying public static void. We need to have obviously a space between that public static. So we have public static void main, and remember, this signature has to be as it is. You cannot spoil this signature. It has to be public static void main. We talked a little bit about this void, that the main doesn't return anything. We have not yet elaborated on what is public, what is static. We will elaborate that in subsequent sessions. So what we do here, now we are going to declare a variable like we do in any other language. We are going to declare a variable of type byte. So let's say byte b is equal to 5. Okay, so let's put in that value there. So byte b is equal to 5. What does this statement do? Let's elaborate a little bit. What does it do? In the memory, now which memory is this? Remember, there are two kinds of memory. One is called stack, the other is called heap. Now byte b allocates memory on the stack. Why doesn't it allocate on the heap? Because if you remember my earlier discussion, if you need to allocate memory on the heap, you need to use the new operator. Only when you use a new operator on a class name, that an object of that class gets instantiated on the heap and a reference is returned to that. That's not what we are doing here. Here when we say byte b is equal to 5, in the internal stack of main, a variable is getting created. The name of the variable is b. So a piece of memory is getting allocated on the stack. So the name of that variable is b. So B is there, this is the name of the variable, and what is the value currently there? There is a value sitting here called B. So B is the name of that variable. Maybe I should not put this. Let's say B is a location on the stack and on which the value 5 is sitting. So now what we'll try and do is, just to illustrate this equation here, we are going to play a little thing with this, a small thing. B is equal to B plus 10. Now this is very interesting, and you will say I am saying byte B is equal to 5 and I am saying B is equal to B plus 10. Now people will ask, that's trivial, and then I am going to print out the value of B, the system.out.println. You know how to print in Java. So we are going to say system.out.println, and we are going to say B is equal to, inside that we are going to say B is equal to, and we are going to concatenate with that the value of B. This is how you do. This concatenates this value to this and prints it out on the output. So let's close the bracket. We haven't closed the bracket yet. And let's run this program. Okay? Yeah. Now before we close it, a few thoughts. Now you'll ask me, or I would like to predict. First thought is, will this program compile? I would like to leave you with two thoughts here before we go for the compilation. I want to make two thoughts clear. A, that basically Java, unlike C++, has a very strong compiler. It's not at all a weak compiler. It is aimed at catching very many things at a particular line itself. Had it been a weakly typed language like C or C++, probably you would have got away with this. Now that is one part. I mean, Java is a very strict language. It doesn't allow trivial mistakes to slip through. That's one point. The second point that we need to understand is, what can be possibly wrong with this statement? And I would like to elaborate. Anything in Java, the default integer data type in Java is int. I would like to just put a tick mark there. The default data type among integer types is an int. The default data type among floating types is f. I'm sorry, it's not f, it is double. The default data type among floating types is double, and the default data type among integer types is int. And I would like to now elaborate on that particular point a little more to get this point through, which is, now if you say B plus 10, what it is going to do is, by default, whenever addition is done on integer types, here B is an integer, 10 is an integer, integer type, the result is always an int, because that is the default type in integers. So what I am trying to say here is that when you do addition over integer types and you have not indicated anything, you have to agree with me that B is an integer type because it is in that family, and 10 is an integer obviously. The result of this would be an integer. So what would happen is that this being an integer, and an integer by default has 4 byte size, and as you know, B is of type byte. So the addition is resulting in the creation of an integer or an int, and on the left hand side of this assignment there is B, which is a byte. So what you are seeing here is, on the right hand side of the assignment statement there is an int, on the left hand side there is a byte. An int, being 4 bytes in size, is trying to get into a byte which is 1 byte in size, which is taboo, which is not allowed, and obviously that's the reason your Java compiler is going to shout at this line. He is going to say, hey, you can't put a fat guy like an int, which is going to be 4 bytes, into a small guy which is going to be 1 byte. So that's the error you are expected to observe. But let's confirm whether we are really and genuinely getting this error or not. So let's do that and see. So we got the file, now we are going to compile it, and hopefully at the compiler level itself there is going to be an error as expected. Here is the answer, which is exactly what I was saying, which is cannot convert from an int to a byte. That is the error you're getting. there's a type mismatch. Now you need to understand what's happening here. That's very important. So here what's happening is this is going to be a byte, there's a byte added with an int which becomes an int. Addition always happens in int. Result is an int. So basically an int is being given to a byte, and that is why the error is coming. Okay. So now let's go back and see whether we can play with this little bit. Let's go back to our program and see whether we can change it a little bit. Okay, let me give you another flavor of this. I'm going to now create 2 bytes. Another byte here, if you will. We'll declare another byte here, which is saying byte A is equal to 10. Okay. Now we are going to do B plus A. Yeah. Now we are going to do this. Now will we get the same error still? Absolutely. Though you are adding 2 bytes, one would normally expect that the result of 2 bytes would be a byte. No. The result of any operation which is performed on integer types is always an int. So when we do this, when we add these two, the result, though this is a byte, though this is a byte, basically the answer is still going to be an int, and you are going to get the same error. Let's see whether this happens also. Now you can see that we are adding 2 bytes and the result is also a byte. But even there, when we compile, you will see we'll get an error because the result of 2 byte addition, though we are not adding 10, we are adding a byte, will be similar. So let's get that error again. So we will compile this file, javac primitive.java. We are back to that same error for the similar reason, that is A plus B, though both are bytes, the result of byte addition is an int, and that's why we are getting a fat guy on the right hand side and a small guy on the left hand side, and it's not able to get in. So this is called actually narrowing. This problem is called a narrowing problem. Why I am calling it narrowing? Because an attempt is being made to narrow the result, and Java doesn't permit this narrowing because he feels that data will be lost, precision will be lost, and that's why he's preventing the narrowing. Can I force this narrowing? Yes, you can. How do you force a narrowing? You force a narrowing by using the cast operator. So we are going to use a cast operator to narrow this. So you see this. Now we are going to come to this line, and he is going to use a cast. Look at the way we use a cast. So we say byte. We have to say byte. This will not solve the problem. We have to put this also in a bracket. So that's how the value is being put in a bracket. So now what you are doing is, you know that the result of this is going to be an int, but you are casting that int into a byte and then assigning it to a B. So the compiler is made aware that yes, I know that the result of these two is an int, and I am forcefully, purposefully casting that result into a byte and then assigning. Now there won't be any error during compilation, and you will get the desired output. So let's compile it. Okay, as expected, our compilation did not give an error, and now we invoke the virtual machine. So we get the expected result, which is 10 plus 5 is equal to 15. So we got the expected result also. So this is very important to understand what is narrowing and why does a narrowing happen. That's equally important. Narrowing is going to happen with byte, short, and int, a similar kind of a situation. Now let's turn our attention a little bit towards floats and appreciate a little between the float and the long. But let's look at the float at the first level. So let's convert our program. Let's drop this program. Let's keep this program safe so that some of you who can come onto the cloud can access it. So we'll create vi primitive1.java. Let's call it primitive1.java. As a second example on working with primitives. So we're calling it primitive1.java. So again, we'll have the class primitive1 and put the appropriate signature for the main method, and then we'll describe this forward. So primitive1, and here starts the class, and we're going to put the main method, public, public, public static void main, Main should have the right signature. And here we go. So we are going to now work with floats. So we are going to put a very simple looking statement first. So we are going to say float f, float, let's not call it f, let's say float k is equal to 10. Now let's put it this way, and let's try compiling this line. Now you will say, what's wrong? 10 is an integer. So now if it is an integer, this would get assigned and it would work. So we would just say print a float. I mean, let's just put a print on the float. That is, I put a very simple statement, float k is equal to 10, because you have to start very simple to understand the nuances of Java. So I'm going to print k, and I'm going to see whether I get the value of k. Okay, so this is how I get. So let me compile it now. Javac primitive1.java. Okay, no problems in compilation, because as we know from this chart, an int is smaller than a float. So let's run it. And as expected, I get the answer as 10.0, because what's happening is the integer 10 is being converted to float 10, and so it's coming with a decimal point. Absolutely no problem. Okay, let's get back to the original program. Okay, here we are. Okay, float k is equal to 10, so I got the answer as 10.0. Very simple. Okay, let's spoil our simplicity a little bit by saying 10.0 over here. Okay, now let's see what happens. And please remember what I said before, that the default floating data type is double, not float. Let's see whether we get any surprises on this line, on this in this program. So we'll try and compile it again, primitive1.java. Okay, so here is a nice error which we get. Now you will say, what the hell is happening? It seemed like a pretty simple statement where we said float k is equal to 10.0. Well, you know, if you correlate and you have been listening to me very carefully, you know what is the error and why is the error coming here. The reason the error is coming here is because by default 10.0 became a double, not a float. I told you the default data type among floats is not float but a double. So what happened? The right hand side was converted by the Java compiler into a double. Double, as you know, is 8 bytes in size and float is 4 bytes in size. So what happened here? The right hand side was converted by Java compiler into an 8 byte operation, 8 byte data type, and it was trying to be converted into a 4 byte data type, again resulted in a problem called narrowing. So this is again a situation of narrowing. Now a lot of people, I have seen experienced Java programmers, look at this line and they don't know why this line is giving trouble. The important point to realize here is this line is giving trouble because 10.0 is being converted as a double by default, because that's the default data type for float, among the floating types. It's becoming a double. There are two ways I could solve this problem. One way to do it is, let's see the first way. So I could tell the Java compiler, hey, I know you are very smart and you would take this as a double, but I want you to take it as a float. The way I could do that is, the first way is I could put an f. This f has a meaning. It is not just f. This f could be uppercase f or it could be lowercase f. We don't care which. The Java compiler doesn't care which. By putting this f over here, what are we telling? We are telling the Java compiler, hey, this 10.0 is a different kind of 10.0. I know, ordinarily if you would look at a 10.0, you would convert this into a double. But I am telling you right now that this 10.0 should not be taken as 10.0 double, which is what would happen by default, but it should be considered as a float. The moment I put in this, basically the Java compiler says, okay, I know what you want. You want this 10.0 to be treated as a double, to be treated as a float, and so I will treat it as a float. The moment you see the f there, you will see the error disappearing. So now let's compile the same program. You saw we compiled the same program just now, javac primitive1.java, and it compiled. There is no compilation error. Let's see the result. So the compilation error went away the moment I put an f there. So we get k is equal to 10.0 as expected. Okay. So maybe just to drive home this point a little more, maybe I would still go and do a little more to this so that you understand what I'm trying to get at. Let's go back to the program again. Now what we will do is let's go back and create another float in our program. Float k, let's call it L. Float L is equal to 5.0f. 5.0f. Okay, now we are having two floats, two legitimate floats, and there's nothing wrong either with this line or with this line. There's absolutely no mistake because we have asked it to be converted to float and then we are assigning it, no problem. So now let's say float m is equal to k plus L. Now, and we are going to print m. M is equal to, yeah. Now, this is again interesting. Now what's going to happen? When this, there's nothing wrong with this, there's nothing wrong with this. But look at this statement. When I have k plus L, because the default data type among floats is double, this k plus L, the compiler is going to transform this k plus L, which is an addition amongst floats. When addition is going to happen, when any arithmetic is going to happen, it is again going to be upgraded to a double. And now I'm going to have my old problem that the double, which is 8 bytes, is trying to be forced into an m, and I'm going to have a problem there. So let's see whether I get that problem. We're going to compile it. Let's go. Let's run it. Oh, we got a correct answer. Go back. Let's see what happened. Okay. Well, I think what happened is a little different from what happens with integer data types. Here, when you added 2 bytes, the integer addition became int, but I guess when you added 2 floats, the type stayed as a float. That means this didn't really convert into an double as was happening in this case, which was becoming an int. So addition on floats, I think, still continues to remain as a float. I think so because the result of this is a float, it took it. Now that's interesting because one would expect that just like in case of short or integers, when you added 2 bytes, you got an int, whereas it showed the same behavior, that by default any data type was considered as a float, and the moment default data type was double, so I was not allowed to give f, and the moment I added, however, the addition was still in float, because I think both were float, the addition remained in the floating space, and then the answer became a float. This is important to remember. Addition of 2 floats becomes a float, addition of 2 bytes becomes an int. And it's interesting to capture this somewhere in your notebook, that if you add 2 floats, you don't get a double, but if you just keep 10.0, the default becomes a double. You need to put in that f there. This is very important. Even I am learning something here. That is, if you add 2 floats, you don't get a double, you still get a float, but if you add 2 bytes, you get an int. Or any addition on int short becomes an int. Okay, so that's something useful learned. Now let's go forward and try another concept which is kind of interesting, and let's talk about what is called wrapping. So we have talked a little bit about narrowing, we have talked a little bit about widening. Widening is the reverse of narrowing, we'll talk about that later. So we are taking another program to illustrate what is called as a wrap. So let's create a third class called primitive2.java, and we'll put in, as usual, a static method. Okay, so let's put some declarations there to help us take it forward. We'll say byte B is equal to 10, which is perfectly fine. Now what we are going to do is we are going to say B is equal to B plus 300, let's say 200. Okay, and then we are going to print B, and then we are going to understand what's the result we are getting. And we will then understand the result. Okay, so let's compile this. I don't think there should be too much trouble in compiling this. So we compiled it. Yeah. Now here's something interesting. Okay, I should have ignored this. I should have taken care of this problem. Again, the same problem. This is becoming an int. I'm sorry, that was not the intention. So we will convert this into an byte. We'll cast it. The intention is to demonstrate something else. Okay. So now there shouldn't be any compilation problem, but I want to show you the result, which is going to be interesting. As expected, there is no compilation problem. So we are going to run it and understand the result. The result is minus 46. Now, what's really happening? Okay, so let's analyze and understand what's happening. So let's go back to our program and see what's really happening. What we are seeing here is an interesting phenomena called wraparound. The phenomena is called wraparound. What's happening? How do you get the answer minus 46 here? Very interesting to understand. See, what happens for bytes is the maximum byte is 8 bits. But though it is 8 bits, 1 bit is gone for the sign. So if you see, byte is, though 8 bits in size, the most significant bit is treated as the sign bit. This is the sign bit. So if it effectively leaves in a byte about 7 bits to contain the value. There are only 7 bits left for the value. The rightmost bit, the leftmost bit, which is the most significant bit, goes for the sign. As a consequence, what really happens is that when we have a value, the maximum value which can fit in 7 bits, the maximum positive value which can fit in 7 bits is 127. And the least value, of course, is minus 128. Now what happens is, if you try to fit in a value which is more than 127, and that is what you are trying to do, you are trying to fit in a value 210 into this 7 bits. Obviously 210 cannot fit in 127. So what happens? It wraps around. How does it wrap around? From the highest value, it suddenly wraps around to minus 128. So when the value goes to 128 here, the value is actually in the byte is minus 128. So when in 210, when the value, imagine you are going up to 210, when you reach the value 128, instead of getting 128 positive, you got minus 128. The reason is, at 127, when you incremented, instead of becoming 128, the byte wrapped to from the highest value to the lowest value. So what would have ordinarily become 128 became minus 128. And then after minus 128, if you understand, the value then started moving upward. How long it will move? The number of positive increments that will happen is given by 210 minus 128, which is 82. So what happens is, it has reached minus 128, then it still keeps incrementing. That means at 127, where we expected the value to be 128, it became minus 128, and then it moved in the positive direction for 82 increments. And net value which became is minus 46. So minus 128 plus 82 is minus 46. That's why you got the answer as minus 46. Now, if some of you are not convinced, you can try this with b is equal to 20. So if b is equal to 20, what would happen? We would get 220 as the value, which obviously cannot come into 7 bits of the magnitude. So what would happen even in this case? It would at 127 or at 128, the value would become minus 128, and after that, instead of 82 increments, there would be 92 increments, which would give a value of minus 36. So what we are saying is correct. If what we are saying is correct, if I change this to from b is equal to 10 to b is equal to 20, the answer I should be getting is minus 36. Let's do that just to confirm this story, that there is a wraparound happening. When the highest value is reached, it immediately wraps to the lowest value. If you create an example where the lowest value is reached and you decrement beyond the lowest value, you basically go back to the highest value. We could demonstrate that also, and I leave that as an exercise. But let's not leave this let's do the b is equal to 20. Can you just come back? Okay, so we have made a small change here, b is equal to 20, to demonstrate this case where the value which is going into a byte is 220. It would reverse at 128 and then it would go for 92 more increments, giving you the net value of minus 36. So let's try this once and see whether we are right. So we'll compile our program. And we would run it. As expected, the answer is coming as minus 36. So I hope all of you understood that on byte data types, like on short data types or integer data types, when the highest value is reached, there would be a wrapping around. Wrapping around doesn't happen on floating and double points. What happens in this case is that when you do a floating or a double, if it goes beyond a particular point, you may get an overflow error or an underflow error. So that there is no wraparound happening on floating data types. Wraparound happens on integer data types. So that's very important to keep in mind, because these small things will come up in different kinds of exams, and it's good to be comfortable, so that good to be very sound on this, because otherwise you'll get surprises when you're doing some basic operations on in your examples. So with this, I would like to just close with another small example demonstrating that long is less than float. So let me just demonstrate that and see this. So I'm going to create another program to demonstrate this, vi primitive3.java, and we are going to write in that code. So it's called primitive3. The objective of this program is just a 2-line program to demonstrate that long is smaller than float. That's an important demonstration, because long is actually 8 bytes in size, whereas float is only 4 bytes. But because of the ability to hold an exponent in float, we'll have float bigger than a long. So we are going to say, and we are going to also see that how do you make a thing a long. So we're going to say long L or long I, long P would be a nice variable, long P is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and now, no, we are not going to put the L there for a moment. I'm just going to illustrate one more thing, and we are going to try and print P. P is equal to P. Okay, and we are going to print this. Okay, let's try this. This is, I have not yet introduced the float, but let's see what happens. So we're going to compile primitive3 and see. Okay, it compiled, and Java primitive3. Oh, I think we didn't make it long enough. Okay, we got the value. Let's go back. Okay, let's make this long enough. I think it is long enough. Okay, so it took this data type as a long and it was able to accommodate. This value would not be possible to accommodate in an int. Let's see now whether we can accommodate this. Okay, let's compile this. Okay, so I think now the error comes out. The point which was coming in here. So see this. What's happening here? Look at the error. The literal, whatever the number that you gave of type int is out of range. That's because just like the default data type for floats is double, I remember telling you that the default data type for integer types is int. So what is happening over here is this number on the right hand side is being converted by the Java compiler into an int, and since an int data type is not big enough to accommodate this, we are getting an error. So what we must do is tell the Java compiler, Mr. Java compiler, don't treat this like an int and then assign it to a long, treat it as a long and fit it in a long. So how do you make the Java compiler look at this number as a long? It's a similar kind of trick like we do in case of floats. By putting an f, small f or uppercase f, we change from double data type to float data type. Let's try a similar trick here, whether it works. So what we are going to say here is, don't treat this value as an int and try to accommodate this into an int. Treat it as a long and then assign it to a long. So now an internal long container is created for this, which earlier was an int container, which was then getting assigned to long. Now there will be a long container created, which will be assigned to long. So let's see whether this compiles and we learn something useful. As expected, it compiled, and this is very important. Let's go back to the program. Okay, let's run the program and then go back. Okay, we got the value intact. Let's go back to the program. Okay, this is very important to understand. If I was not putting out this law L, this value was first assigned to an int or put in an int, and then it was assigned to a p. But the problem came when I was trying to assign this to an int. This int data type is not big enough to accommodate this value. Now when I put L, the right hand side first became a long instead of becoming an int, and then it was assigned to a long, no problem. So this is very important to understand. Now I would say I would declare a float f or float k. K, okay. Now let's give a value 10, some optional value 10, or let's give a value p. Sorry, let's give a value 10. Let's give a value 10. 10.0 or 10.0f. Okay, let's go to the next line. Let's go to the next line here. Okay, now let's try to do something interesting. Now you're seeing long holding such a big value and a float holding such a small value. Now let's try to say p is equal to k, and let's see whether this line works fine. Okay. I have a problem as expected, because though the p is right now holding a very big value, the problem is k is a float. So k is treated, a float is treated as a bigger than a long because of the ability to hold an exponent. So what's this situation again called? This is again called narrowing. This is again narrowing because float is assumed to be bigger than a long. The long is 8 bytes, float is only 4 bytes, but because of the exponent, the compiler decides that, hey, on the right hand side there is a fat guy called float, which is bigger, and on the left hand side there is a long, so I'm not going to allow this to happen. So this is very important to understand. Let's go back to the program to paraphrase this problem. See this, the long is capable of holding big values and we are putting a very small value in float, but this line still doesn't work because the compiler thinks float is potentially capable of having a much bigger value, and it cannot go into a long because long is treated by the compiler as smaller than a float because of that ordering system that I asked you to memorize in the beginning. So this is treated as narrowing. Narrowing is not permitted. How can I solve the problem? You know the solution. So we can just cast the k into a long and tell the compiler, I know float is bigger than a long, but I want this value to be treated as a long, and there we are. So we are casting it into a long, and we solve the problem. So we are overriding the compiler and telling him, I want this value to be treated as a long. So we compile it now. We get the compilation through as we just saw here, no errors, and we run it now. As expected, we get the answer as interesting answer as 10. Now why did we get 10 as a result? Let's go back. Okay, we got the result as 10 because k was a float 10 which got cast into long. There was no truncation, and we got a 10. So that's the reason we got that answer as 10. Okay, so this is how what we have demonstrated here is some basic behavior on primitives. We'll talk more about this in subsequent sessions.